Welcome to Physics 371 Online. The last section, in Chapter 1 of the text, takes a step back and helps us answer the question, why are we spending so much time studying the gradient, divergence, and curl of vector functions? It's always a good idea to stop for a moment, take stock, before we move on to the next part. The theory of electromagnetism, as you already know from your previous studies, is expressed in terms of the electric and magnetic fields that are produced by electric charges and currents. And it turns out that if we know the divergence and the curl of a vector function, or a field, along with appropriate boundary conditions, we can actually uniquely determine the field itself. And this is why much of the mathematical apparatus of electromagnetism deals with divergences and curls of electric and magnetic fields. We can make this assertion somewhat more formal in the form of the Helmholtz Theorem. The Helmholtz Theorem says as follows: if the divergence d of r and the curl c of r of a vector function f of r are specified, in other words, if we know what they are, and here's the boundary condition part, if they both go to 0, d and c, faster than 1 over r squared as r goes to infinity, and if f of r goes to 0 as r goes to infinity, then f of r is uniquely specified. And that's a fancy mathematical way for saying that we can calculate it, that we can solve for it. And this is the topic of Appendix B in the textbook. So if you'd like to see the expression for f of r in terms of d and c, the divergence and the curl, you can look at the appendix. Some special cases, it's worth noting, are the two extreme cases for fields, first of all, whose curl is equal to 0. There are 4 properties, including simply the statement that the curl of f is 0 everywhere, but there are 4 properties that all imply one another. So if the curl of f is 0 everywhere, then that means also the line integral of f dot dl from a to b is path independent for any points a and b. And trivially, what follows from that is if a and b are equal, in other words, if you integrate around a closed path and end up where you started, then that line integral is going to give you 0. And finally, an equivalent statement is that this vector f, whose curl is 0, can always be written as the gradient of some kind of scalar function v. It can't just be any function, but there does exist a function v whose gradient is equal to that function f. So the second case is a kind of field where the divergence is 0 everywhere in space. Not only then is the divergence equal to 0, but a consequence of that is if we integrate the flux of that vector field over a surface, that flux integral is independent of the surface for any given boundary line. So once the boundary line is specified, any surface that is bounded by that line gives you the same result. Therefore, if you do the integral over a closed surface where the boundary line vanishes, you necessarily get 0. And finally, similar to the expression above, f can be written as the curl of some vector function a. So these two special kinds of fields, one that has no curl, the other that has no divergence, can be written in terms of, in one case, the gradient of a scalar function, and then, in this case, the curl of a vector function. And we will come back and see these expressions again in our study of electric and magnetic fields. So, that's a very quick overview, but the Helmholtz theorem makes it clear that if we know divergence and we know the curl of a vector function f, then, along with sufficient boundary conditions, we know what f is. We'll see you in class.